Hey kids, Smath here. Going to give you a little walkthrough on the Diagnostic Test I. Now, I realize some of this was very challenging material. So what I've done to help us out here is I've color coded the numbers by either green, red, and you'll see on the other pages, yellow. Green would mean green is a good question. Red means that question is irrelevant. Either A, it's too specific and factual, or B, that it's material that may not be covered on this year's exam because it's in units 8 or 9. But green questions are good questions. And what it balances out to be is about half of this was pretty good stuff. The other half of it was just to kind of keep us thinking about chemistry. Even though it's not a good question for this year's AP, doesn't mean it's not a good question to be thinking and learning about chemistry. So let's go through some of my solutions here. So the first question asks us, a solid of aluminum carbonate, Al2CO3, is strongly heated to make CO2. This is going to be a reactions question that turns into a stoich question. That CO2 is then bubbled through sodium hydroxide, forming sodium carbonate and water. So they told us what this makes. So the first thing I did was I came up top here and I wrote both reactions. Al2CO3, that's a carbonate. Carbonates decompose into oxides and carbon dioxide. I had to balance it out. Watch that, 3 CO2s. I'll always have as many CO2s here as I had carbonates there. So then I took that CO2, put it into sodium hydroxide. Now this one's a little bit hard if I had to predict it, but they told us that this made sodium carbonate and H2O. So in that case, I just had to balance and I needed that 2 in front of the NaOH. So now let's get to the stoich part of the program. Stoich said I had 0.6 moles of aluminum carbonate. So now I take that 0.6, that means I'm gonna make 3 times that amount, 1.8 of CO2. Take that 1.8 CO2, I'm gonna need twice as much NaOH. That gives me an answer of E. It's a great problem. We have to write some reactions, balance some reactions, do a little bit of simple stoich. I like that one. I thought it was pretty cool. Okay, number 2, still a green problem. We have a sample of nitrogen trichloride. And this one is a cool demo that I would probably do for you guys, that you make this and then it's a pressure sensitive. You make it, you let it dry, and when it dries, if you tap it with like a meter stick, it kind of pops like a cap. So exploding's a little bit over the top, but it says a sample of NCl3 0.1 moles explodes according to the reaction. What's the volume of gas? So if I had 0.1 moles of the NCl3, then for every 2 of these, I get 1 of those. So I'm going to get from 0.1, I'm going to get half of that, 0.05 of the N2, and I'm going to get 3 times the amount. 3 times 2, okay, is going to give me 0.15. So both of these are gases. So what they want to know is, what is the volume of the gaseous product? Both products are gases. So I have to add together these 2 moles to get 0.20 moles. And because this is at standard conditions, 1 atmosphere and 273 Kelvin, I can use 22.4, and 0.2 times 22 is going to give me an answer of about 4.48. Really good question. A little bit of stoichiometry, a little bit of gas laws. I still think way too computational, but I don't know. We're predicting this year's exam. 3 is another gas law question. This one about under what set of conditions. So we're going to say deviation from the ideal gas law. Well, start with the ones that we know for sure. When do things deviate? When do they behave real? When do they have intermolecular forces take over? That's going to be when we slow them down, get that temperature low, and we smash them together, bring them in real close, real tight, okay? So high pressure, low temperature. So in that case, it's got to be low, high. Well, in that, it doesn't matter then. The size of the molecule is insignificant. But Why would the size of the molecule matter? Because the larger the molecule, odds are the more electrons it's going to have, and the more LDF forces are going to take over, the stronger the LDF forces are going to take over. So that was another good green question going on here. Now, four is just talking about the type of bonding. It's a red question, not because it's off of the chart with units 8 and 9, but that it's just a very finicky type of bonding question. So I'm not even going to go over that one. Not worth our time. Okay. 5 is another green question though. 5 is about rubidium. Rubidium is less electronegative than lithium. Okay, now this one's kind of fun because what we have is we have lithium up top, we have rubidium further down. So we're going down the periodic table here, and it says, nope, I don't want that. I want to blow this up a little bit so we can see it. Rubidium is less electronegative than lithium, all right? The electron that's lost in order to form a stable rubidium ion. Well, rubidium's further down the periodic table, therefore it has a lower ionization energy than lithium's valence electrons. Has nothing to do with radioactive decay and has nothing to do with charge since they're both in the same column. Okay? So 5, good question. To be honest with you, I think a very straightforward, easy type of question. I'm expecting you guys to test very well on that. Now 6 ends up being our first yellow question. Is yellow fair game? Yes, but it kind of is a yield, okay? This is like a stoplight. Red is stop, green is go, yellow's kind of, I don't know. So for which of the following will dissolve in concentrated hydrochloric acid? At first I looked at this and I thought, gee, this is going to be a hard question for us. But then I started just saying, okay, well, what are the products? If I just put HCl on the outside of this, and I just say HCl, 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 what do I get? Well, the thing I get in reaction 3 is HCl and NaCl are going to produce HCl and NaCl. That's the no visible reaction thing going on. So then I just have to say, okay, so 3's out of the question. So I can throw out, what about 1 and 2? Well, calcium carbide is tough, but if we throw carbide in with HCl, I know I'm going to get calcium chloride. And then what's left? I get this acetylene gas, C2H2. The only reason I know this, we did this in our types of reactions. We took carbide and put it in water, and then we lit that test tube on fire and burned this acetylene gas. It's a reach. That's what makes it a yellow question. Okay, what about our CUS? That's going to make H2S and CuCl2. That's pretty straightforward ionic chemistry. I think we're doing okay there. So our answer there should be 1 and 2 should give us good answers. 3, no visible reaction because it makes the same thing that it was starting out with. So that's kind of useless. 7 is another yellow question. And 7 says, according to the overall reaction, what's going to happen? Well, the decomposition, the slow step is the O3. So what's going to happen to the reaction rate if the pressure of the ammonia is doubled? Well, you're still increasing a reactant. So by increasing that reactant, I want to say it's going to increase by 6/5. But the more I think about that, I don't know the mechanism. So I'm going to change my answer on this one and say, you know what? I don't like that. I'm not really sure. I'm not really changing anything having to do with the rate determining step. All I'm doing is changing the NH3, and we don't know the rest of the mechanism. So if it doesn't change that, the rate probably is not going to change. The rate is determined by the slow step. They didn't change the ozone pressure. They changed the ammonia pressure. That's changing a faster step. We're not concerning ourselves with faster steps. Kind of interesting. Don't know. But that's my best answer. It's going to remain the same. Okay, let's look at 8. 8's a red question, probably not going to show up. Now, in this case, it's not showing up because this was in chapters 14, 15, unit 8 for sure, acid and base. But we wish it would show up. This is a great question, pretty easy question too. What's the pH of this solution? If we take we're taking the same volume, 5 mils, in this case, of a higher concentration of a stronger base. This is going to be strongly basic. Come on, there's not much argument there. It's red. I wish it was green. I think it's a pretty good question, but a lot of people didn't get to this, so that's okay. Now 9 is another red question, and it's red because of the vocab terms that's used and because the AP took this stuff off when they quit using the terms reducing agent and oxidizing agent. And so in this case, for the following reaction, identify the element being reduced. I think that's a fair question. So I just put my oxidation states up above the nitrogen and the carbons. The carbon goes from 2 to 4, that's oxidized. The nitrogen goes from 4 to 2. Oxygen is staying -2 in all cases here. So the nitrogen is being reduced. And what must be doing that? The reductant is called the oxidizing agent, the thing that's doing that. And so that must be the carbon monoxide. And that's why I came up with that. Okay, so that's a red question. AP doesn't like it. I think it's okay. 10 is one that we wish could be on there. It's just the chart from chapter 17 that says, when are things going to be spontaneous? They tell us that this is a spontaneous reaction, therefore delta G is negative, and that H is negative. Well, if H is negative and G is negative, S can be positive or negative depending on the temperature that's involved here. So that's why I chose the answer that I chose, which was D. S can be positive or negative, not on the board though. 11, a yellow question, little bit sketchy. They used to make a big deal. This is obviously an older test. So they used to make a big deal out of this red-brown gas. Red-brown gas is NO2. Even if we didn't know that, when lead nitrate is decomposed, we take what's left and we get an acidic solution. That acidic solution I'm looking for is HNO3. Here I got some HNO3. I kind of like that, but I didn't get the red-brown. So A is a good answer, not the best answer. B, I got the brown gas, but I got HNO2, a weak acid. Probably not going to dissociate like that. In C, I got the brown gas and I got the HNO3 dissociated because it's a strong acid. That's my best answer. Let's look at D. In D, I didn't get the brown gas and I didn't get the strong acid. Not a good answer. And in E, I got the brown gas and I got the strong acid, but look what I got with the strong acid. The strong acid. That's very strange. There's no reason that you would have the same substance dissociated and undissociated in the same reaction. That's ridiculous. Not going to happen. Okay, so C is my best answer there. We're over halfway. Stick with me here. 12 is isomers. Isomers are off the board. Haven't been for a while, but what they are different molecular arrangements of a compound. So it wants to know how many distinct isomers are there. There is no formula to this. I wish I could tell you that it's, oh, take the number of carbons, square it, take the second derivative, and that's how many isomers you get. No, it doesn't work that way, kids. Sorry, you just have to draw them out. And so that's all I did here is I took the isomers, I took the 2 carbons, put them in the middle. I took the 2 carbons, put them on the end. I took the 2 carbons and put 1 on each end. You get 3 isomers. Someone's probably saying, well, why didn't you take the 2 carbons or 2 chlorines and put them over on the other end? That's the same molecule just flipped around. That doesn't count, okay? Want to learn about isomers? We'll do that a lot more when we do Orgo next year. In this class, we're not talking too much about isomers, but your answer there was 3. Okay, let's keep moving here. 13 is a green question, and it's a darn good green question because it deals with precipitation, okay? And a little bit of acid base, which I think is just fair enough. 13 says, I've got a 0.1 molar aqueous solution of a white crystal. Yeah, okay, great. That doesn't help me at all. What helps me is it precipitates out when we threw it in silver nitrate, okay? And when we put it in phenolphthalein, it turned pink. So we knew it was basic. So now let's go through. Each of these, excuse me, get recentered. Each of these is a salt. These are all salts. We need to figure out whether they're acidic salts or basic salts. NH4 and Cl, that's going to be acidic because NH4 comes from a weak base. Cl minus comes from a strong acid. You know what? Now that I'm thinking about this, I'm going to recant my green. It's weak and strong. Weak and strong is not going to be on this year's. But we did it. Dadgummit. Okay, so this is going to give me an acidic solution. K3PO4 is going to give me a basic solution because KOH, H3PO4. And it's going to give me an insoluble Ag3PO4. We like that answer. Why not KNO3? KNO3 is neutral, comes from a strong base, KOH, HNO3. NaCl is neutral, comes from NaOH and HCl. NH4ClO4 is going to be asoluble, but also going to be acidic from HClO4 perchloric, which is strong, and NH4 comes from ammonia, which is weak. So that one's not going to work out too well. But it's a red question. I recant my green. Okay? 14, radionuclides. A fair question, but really not going to show up. They get 2 questions for this year. They're not going to waste one on radiation. We did radiation very briefly in chapter 2, I believe, when we did atomic structure. But basically the key here is it uses the term, what is non-penetrating? Non-penetrating is alpha. Beta particles and gamma particles are penetrating. Thermal particles, I don't know what that is. That's just, I don't know. Kappa particles, it sounds like a fraternity or a sorority. Not a chemistry thing. So your best bet, non-ionizing radiation, alpha radiation. You could block alpha radiation with a piece of paper. Very simple. Okay. 15 is a green question. And this is solutions and number of ionic particles. So it says, which of the following is going to have a similar boiling point? So when we talk about boiling points now, we're talking delta T equals K M I. So what we're looking for, since we can't change the K, we're looking for this combination of molality to, or molarity, molality, it's not going to differ too much, to ionic particles. And so we had a 0.2 molar solution of sucrose. So that's 0.2 molar times 1 particle. Well, that's going to be 0.2. If I go through the rest of these, I have 0.2 times 2 particles. That would be 0.4. I have 0.1 times 4 particles, K3PO4. So that's going to be 0.4. That's probably going to have the highest of all of these. 0.1 times 1 particle. Acetic acid is a weak acid. Not going to help us. 0.4 times 2. I take it back. That's going to be 0.8. That's going to be the highest of the boiling points. Okay? The one that ends up answering our question, take 0.1 molar and split it in between 2 particles. That's going to give me 0.2. Okay? So that's a good solution colligative properties kind of question. Kind of neat. Stick with me. We got 4 more left, and I get rid of that. Here we go. Now there's a couple of red going on here, and we don't need to spend too much time on those. 16, most likely to transform. Here's the deal. And this one is a reactions thing. It's that this MnO4 is an oxidizer. It's got so much oxygen in it. It's a strong oxidizer. So it's often used for in this case, a redox type of question, okay? But not gonna come up, all right? The 17 is a buffer question. We should be able to get this right. Here's what we've got. We're looking for a weakly acidic buffer. Strong acid, strong base, and a strong acid. Throw that out. So what we're left with is H2S, which is a weak acid by itself, or the good answer, which is a weak acid here, looking kind of ugly. This is another way of writing acetic acid with sodium acetate. That's going to give me a weakly acid buffer. But that's a red question. Not going to show up. Just teaching chemistry here, kids. Okay. 18, good question, easy question. Would expect a lot of success on this. It's the ground state, so we're not skipping anything for the given element or ion. Iron is good, nitrogen good, oxygen ion, yes, it ends in S6, okay? A chlorine cation. Good luck doing that. It's going to take a lot of energy, but we're going to take a P5 and remove an electron. This is still correct. Which one's not correct? Al3 plus. No, that's not your 3 plus. You're going to have to take away more, okay? You're going to have to take away both of these 3s2s and end up with a 2p6. This wouldn't be ground state anyway. So good question, easy question. You guys should be finding that one. All right, 19's another one. 19's a bonding question. Which one's most likely to have a 1-to-1 ratio? So alkali with chalcogen, +1 - 2. Alkaline +2, halogen -1. Alkaline +2, chalcogen -2. Ding, 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 that's a 1-to-1 ratio. Transition metal, yeah, we don't know. To either a -2 or to a noble gas. So +2 - 2, great 1-to-1 ratio for you here, kids. Okay. And last but not leastly, we got a red question. The Hull-Heroult process is one that used to show up big. It doesn't anymore. But let's walk through how you could get the solution. You really don't have to know anything about the Hull-Heroult process. They gave this to us. It basically says carbon is consumed. So if the carbon is consumed, the aluminum at the other is going to be deposited. If the aluminum gets deposited, what do I mean by that? What I mean is Al3 plus is being deposited as Al. This reduction is happening. So we could have figured it out. It's not going to show up on this year's exam, but it's an interesting kind of question. So what you have there is some pretty good solutions, pretty good explanations to AP Diagnostic 1. Was it meant to be diagnostic? Not necessarily, because nothing this year is going to help us be diagnostic. We just have to learn and try to apply as much chemistry as we can. I've gotten you answers to these. I think as we get into AP Classroom, we're going to see more pertinent type of questions, and those should be happening very soon here in the future. I'm Smath. I hope this video helped.